I'm very happy to be back in Cornell. So I will be speaking about the exponential functions of Lévy processes, as Pierre already said. In fact, there will be not many self-similar Markov processes in here, but the motivation for studying these functionals is coming from the theory of self-similar Markov processes. So this is based in a joint work with Jonas Orisa from CIMAT, a PhD student, and the second part with Andreas Cipriano and Vera Pat Satik. Sorry, I practiced yesterday, I couldn't do it. Okay, well, this was the second part. Okay, so let me start by introducing some notation. Okay, so I will be considering psi a real valued Lévy process, which is scaled at an independent exponential time of parameter q. I will allow q to be equal to 0, so that the lifetime of the process is infinity almost surely. Okay? I will consider that the process, when it is scaled, is sent to the state minus infinity. Okay? And I will denote by set the lifetime of psi. Okay? We know that the Lévy process psi is characterized by the characteristic exponent psi, okay, by this formula, and that psi can always be written in this form. Okay? So it's a usual representation, Lévy representation, plus the killing term q. Okay? And these four terms should satisfy that q is positive or 0, a is a real term, and sigma is another real, and pi is a Lévy measure, and it should satisfy this integrability condition, the usual one. Okay? These four terms characterize the process. Okay? And I will be always assuming that either q is strictly positive or q is 0, and the process drifts to minus infinity. Okay? And under those assumptions, we know that this random variable called the exponential function of psi, so the integral between 0 and infinity of the exponential of psi over the whole lifetime interval, is finite almost surely. Okay? And in fact, these two conditions are, either of these conditions are necessary and sufficient for this random variable to be finite. The reason for that is that when q is equal to 0, the Lévy process grows at least linearly. And when q is strictly positive, we are just observing the path of psi over a finite length interval. Well, these random variables have applications in the theory of self-similar Markov processes. There is a very strong connection with that theory. But it also appears in the theory of Brownian diffusions in random environment, in mathematical finance, in self-similar fragmentations, in composition structures, and in many other places. Okay? And well, the problem is that there are just small numbers of families of these random variables where the distribution is explicitly known. And the reason for that is that we are observing the whole path of the process, okay? And it's difficult to get information about the random variable. So it's important to get methods to understand this random variable. And there is a seminal paper by Carmona, Petit, and Yori in 1997, where they started a systematic study of these random variables. Okay? And after that, there has been a lot of research activity to try to understand this family of random variables. Okay? So what I would like to do today is to introduce a new formula that will help us to derive other results. But I will first mention some of the results that are available in the literature. I won't be doing an extensive review of the theory because there have been a lot of activity. I will just mention three important results. Okay. The first of them is what I call an integral differential equation that was obtained in this paper by Carmona, Petit, and Yori in 1997. They prove that if the Lévy process psi has an infinite lifetime, the young part is a bounded variation process, so it's the difference of two subordinators. Okay? And the Lévy measure satisfies this integrability condition, and also that the mean is finite. Then under those assumptions, they managed to prove that there is a density for the random variable I, and in fact it's a C-infinity density, and it's the unique probability density function that solves this equation. Okay, so there is a differential part coming from the Brownian motion plus the drift, and there is an integral part coming from the jump part of the Lévy process. And well, this equation has been generalized to other Lévy processes. Okay, has also been generalized to exponential functional driven by two Lévy processes. Okay? So we can find results related to this equation in papers by Bemmel, Linder, Snetsov, Pardo, Batiste, above many other people. Okay? In fact, well, this equation looks nice, but in fact it's very difficult to solve it. We have a differential part and integral part. It's very difficult to get explicit solution to that. I think it's only in the Brownian case where when there is no jump part where we can easily solve it. Right? But even if you go to the compound Poisson case, this can be quite difficult. Okay. Nevertheless, we can use this equation, okay, to get some asymptotic behavior of the density, both at 0 and at infinity under some assumptions. And well, that is something nice. We managed to do that in a paper with Juan Carlos Pardo and Kish van Schaik for the behavior at 0. I will come back to that later. Okay, and for the behavior at infinity, we managed to use it for subordinators. Okay, in a paper with Benedict As in 2012, in a work with connection with quasi-stationary distributions of self-similar Markov processes. Okay, there is another in that paper of Carmona, Petit and Jor. There is another formula that was later extended by Molik and Schwartz in 2006 and by other people that establishes that the moments of I, so moment I beta, satisfies this relation. Okay, so there is a recurrence relation for the moments of I, okay, and this is true for all beta complex, such that the real part of beta is strictly positive, and this, so then the characteristic function is such that these values more than 1. Okay, and this formula is very useful. I think that most of the theory that has been developed in the recent years is based in this formula. Okay? And it has been used, for instance, by Molik and Schwartz and Gehr and Laden to write the Mellin transform of I as generalized by Strauss products. I think Laden may be speaking about that tomorrow, possibly. Okay. And it has also been used to obtain series expansions for the density for some families of Lévy processes. There is some nice paper by Pierre in 2009, another one by Alexei and Juan Carlos in 2013. Okay? And there are many, many other consequences. In particular, it's, this formula can be used to observe that there are some factorizations that arise for these exponential functionals. Okay? So I will speak about this in the next slides. And the reason for that is because it's part of the motivation of my research. Okay. So in the particular case, when we take psi, that is a negative of a subordinator, so psi is non-increasing. Okay? The exponential functional, the moments of the exponential functional can be written like that. So the product of k divided by phi. Phi is the Laplace exponent of the subordinator. Okay? And from here we can see that the exponential functional has exponential moments of almost any order, for up to order betas more than infinity. So if the subordinator is a compound Poisson process, this phi infinity will be finite. But in other cases, it will be infinite. And that makes that the law of I is completely characterized by its entire moments. Okay? And there's one simple remark here, is that this n factorial, okay, is in fact the end moment of the exponential random variable. Okay? So one may wonder if there is another random variable r, okay, such that its moments are given by this product. Okay? If that is the case, then we can take independent copies of I and R, okay? And we will find that the product of those random variables will follow an exponential distribution. Okay? And this can be useful because if we know something, for instance, about R, we can say something about I, and vice versa. Okay? Or if we know something about some random variable that satisfies this relation, we can try to see if this is related to an exponential function of some Lévy process. Okay? So this question was answered by Bertrand and Jor in 2001, and they proved that for any subordinator, there is always such a random variable, so a random variable that satisfies, whose moments satisfy this relation, so this recurrence relation, which is similar to the one for the exponential function. And this makes that the moments of R are given by the product of phi. Okay. And as I said before, if we take independent copies of I and R, we get that the product gets an exponential distribution of parameter 1. And well, in a paper by Hirsch and Jor, they call this random variable the residual exponential function associated to the subordinator sigma. Okay? I will be calling like that, the random variable all the time. Okay. Well, in fact, this formula that we have here, we can also write it in terms of the densities. Okay? And it will look like that. So we'll take that the law of R size bisect by 1 over t, okay, will satisfy this equation. Okay, so the law of R satisfies this relation. This measure V is the potential measure of the subordinator. And the reason for that is that the Laplace, we can see that this potential measure should arise is because the Laplace transform of V is just 1 over psi flat. Okay. So this term that is here will relate it to this the potential measure of the subordinator. Okay, so we can check easily that this equation is satisfied. Here, I mention it just in the case where the subordinator is killed, okay? Because in that case, this measure that I have here is a probability measure, but in fact the equation is true in general. Okay? And here there is another random variable that is appearing, because when we take phi 0 to be strictly positive, so when the subordinator is killed, this measure V is a finite measure. The potential measure is a finite measure, and this looks as a product of two random variables, exponential of minus y and r. And so we get that if we define a new random variable, g sigma, by this transformation, size bisect 1 over r, this random variable g sigma should be equal in law to the exponential of v, where v follows the distribution given by the potential measure. Just another expression of this formula is this equation in law. Okay? It's another factorization that disappeared. This will be important in the next slides. Okay. And then, after these results, there has been a series of papers by Carlos Pardo, Pierre Paty, and Mladen Savov in 2012 and 2013, where they prove, using the moment formula, that the exponential functional of a Lévy process psi can always be written as the product of two independent random variables. One is the exponential functional of the downward ladder height Lévy process, the subordinator. Okay? So we saw that before in the talk by Alexei. So we draw the path of the Lévy process, and there are two subordinators that arise. The first one will describe the supremum, okay, in a different scale of time. This one is h, the upward ladder height. And there is another one that is describing the Vimon. This is H hat. So that's the downward ladder height subordinator. And the other random variable that's appearing in the factorization is the remainder exponential functional of the upward ladder height. Okay, so it's the only one that satisfies this solution, okay, where I is given by the exponential functional of minus the upward ladder height. So they prove this interesting equation, so which is just mirroring the Wiener-Hoff factorization of psi. Okay. The JH is, as I said before, given by this formula here. Okay. And well, how they observe this this identity, no? In fact, well, the Wiener-Hoff factorization, as Alexei told us before, tell us that the characteristic exponent of psi can be written as a product of the characteristic exponents of h and h hat, so kappa and kappa hat. Okay. Well, this is depending, Q is depending on the killing rate. And if we apply this formula in the moment formula of Carmona, Petit, and Yor, we see that there is this factor that is appearing here in red. Okay. But that factor is also appearing in the moment formula for the exponential functional of the downward ladder height. Okay, so this allows to infer, okay, that this Mellin transform can be somehow written in terms of the Mellin transform of the downward ladder height, the exponential functional of the downward ladder height, okay, and something else. And well, they managed to write the other term, this JH, as an exponential functional of a spectrally positive Lévy process, whose existence was not always guaranteed. But then later in the paper in 2013, they managed to identify this as a reminder of the exponential functional of the upward ladder height as subordinate. And my motivation for the research was try to understand better how the Wiener-Hoff factorization was giving place to this factorization. Okay, this factorization we have here. Because, well, I tried to understand that before I knew the final version of the factorization, because it seemed that it was something that had to work in all the cases, and you had it first under some assumptions. So I wanted to understand that better, and the other reason for trying to understand that better was that I wanted to obtain extensions of these factorizations to, instead of having a Lévy process, having a Markov additive Lévy process. So I will tell you another proof now that we can derive from this. And yeah, so from this formula, okay, so we are seeing that we have to have a good understanding of the Wiener-Hoff factorization. And another way to have a good understanding of the Wiener-Hoff factorization is not via the characteristic function, but via the measures that are associated to this. And the measure that is associated to 1 over psi of lambda is just the characteristic function of the potential measure of the Lévy process psi. Okay? So we take u dy as the potential measure of the Lévy process psi. We know that the characteristic function is given by 1 over phi. Okay? So this term that is here should be related to the potential measure of the Lévy process psi. Okay? So we have to kind of invert that formula, and we'll get something like that. So we'll have that the tail distribution of the exponential functional of psi can be written as a convolution of the density and the potential measure U. We first prove this identity in the case where psi is non-increasing in a paper with Juan Carlos Pardo and Kees van Schaik. To prove that identity, we actually work with the moments, but in the general case, we don't have that technique. But we managed to find an easy proof that I will just show you in the next slide. In fact, we don't have to prove that the density exists. That the existence of the density was obtained by Bertrand, Linder, and Mahler in 2008 in a paper. And the proof of this identity, because we cannot just invert the moment formula, we can do it like that. So we take first 1 minus exponential of minus lambda I, the exponential function, and we write that as an integral of the tail distribution. And then this term that we have here, we can write it in this formula, in this form, just because this term is the derivative of this term here. Okay? And then we can multiply and divide by the exponential of psi t. But this term, because of the property of independent and stationary increments of psi, is a copy of the exponential functional that is independent of all this part. Okay? So now, if we integrate, okay, we will get something that will be very easy to invert, and that will give us this identity. So this works in general, and in fact, this can be easily generalized because we are just using the property of independent increments, in fact. Okay. Well, this formula that I mentioned has several applications. First, we can easily get the moment formula of Carmona, Petit, and Yor. We just have to take the Mellin transform in each side. Okay. We can also work a little bit with some properties of the measure U to get a more general version of the integral differential equation of Carmona, Petit, and Yor. And well, there are other results that can be obtained, like some asymptotic estimates that I will also describe later. And well, with this formula, what I wanted to do also is to try to get a proof of the formula, factorization formula of Pierre, Laden, and Juan Carlos, and it's possible to do it. I will tell you now how to do it. Okay? And this also gives us some ideas about how to generalize these results for Markov additive processes. I will define later what is a Markov additive process, and I will tell you the form of the results. But okay, so to give you an idea of the proof by of the result by Laden and Pierre, so we have to observe that the potential measure of the subordinate of the Lévy process psi can always be written as a convolution of the potential measure of the upward ladder height, which is this B plus, and the potential measure of the downward ladder height, just is a negative convolution. Okay? So that is because of what Alexei said before. We can write the law of x at an exponential time as the law, as the sum of two independent random variables. One is related to the infimum, the supremum, and one is related to the infimum. The parameter here will change, okay? But when we make q equal to 0, which is the we will get the potential, okay? We will get the potential for each of these sides, and this is in fact related to the here is exponential. But in fact, this can be also written as h at an exponential time of another parameter, and h hat of an exponential of another parameter. Okay? But when we make q go to 0, the parameters will not play a role. Okay? So we get this formula from here. Okay? And in fact, because we're assuming find something?
No, I don't.
Well, because we are assuming that psi is drifting to minus infinity, okay, the overall supremum will be finite almost surely. Okay? That means that the awkward ladder height will have a finite lifetime. Okay? So there is an absolute supremum for the whole path. Okay? So that is meaning that's saying that the awkward ladder height is a killed subordinator. Okay? And in fact, the law of the supremum is given in terms of the potential measure P plus. We have this formula, and well, we can write this formula in a simpler way when we have some more information about the jump measure of psi. So for instance, if psi has no negative jumps, so pi of minus infinity 0 is equal to 0, V minus will be just the Lévy measure. Okay? And if psi has no positive jumps, so pi of 0 infinity is equal to 0, V plus will be just an exponential density, okay, of the Lévy measure. So that helps a lot. Okay? And well, so we can now give a proof of the identity. So we just need to observe that we have a formula for the exponential functional of the Lévy process psi. It's written like this. Now I use the Wiener-Hoff factorization for U, and I write this as a convolution of B plus and B minus, and the density of I evaluated in T exponential B minus A. Okay? So this term in blue is coming from the upward ladder height, the one in red is coming from the downward ladder height. And I know also that the equation, I can apply the equation for the exponential functional of the downward ladder height. It will look like this one, so if you see, they look similar. Okay? And I also have a formula for the remainder, where the awkward potential measure is given. Okay? And we just have to write the probability that the product I, H, and J, H, defined like this, is bigger than T. Work a little bit and we'll get easily a proof of this identity. Okay? And this is giving us something else, because I told you before that JH can also be written as the exponential of a random variable V, but in this case V is the law of the supremum, has the same law as the supremum, and then a product of IH and 1 over RH. And this extra identity that we get for free from this expression here is validating a conjecture that I have a long time ago, that is that the large values of I should be coming from the large values of psi. Okay, so from the large values of the supremum of psi. In fact, yeah. So we can, in many cases, we can see that the tail distribution of phi is determined by the tail distribution of the supremum. This factorization of Pierre and Laden can be used to study several properties of the exponential functional. So one nice application is to study the multiplicative infinity divisibility of I. Okay? Because we know that the random variable, the remainder random variable, RH, is always multiplicative infinitely divisible. And more, we proved in a paper with Lévy and Markov that this random variable RH can be always written as an infinite product of random variables that can be expressed in terms of the overshoots of the Lévy process psi. And we can also extend that result to, under some assumptions, to the exponential functional of the downward ladder height subordinator. For instance, we will have that this random variable is not always infinitely divisible in the multiplicative sense. There are some examples where this is not true. But for instance, if this product is a completely monotone function, then the random variable will be infinitely divisible in the product sense. And we will also have a representation like this one. Okay? So we'll, from that condition, we'll get that this random variable I is infinitely divisible in the multiplicative sense. But still, this is not a necessary sufficient condition, and there is an open question that I don't know if some of you have a clue about it, is what are necessary sufficient conditions for this random variable to be infinitely divisible in the product convolution. Now let me speak about some applications for to describe the behavior of the distribution of I. Okay? And for that, I need to recall that this potential measure U is in fact a renewal measure in the usual sense, because we can always write U as a sum of convolutions of F, where F is the distribution of the Lévy process at an exponential time of parameter 1. Okay? So this equation, in terms of this equation becomes a convolution equation. Okay? So we can apply the renewal theory to study this tail distribution easily. This is something that is not completely new, because it is also known that the exponential functionals are examples of perpetuities. And there is a paper by Goldie, which is called Implicit Renewal Theory for Perpetuities, where he derives something similar. Okay? But in this case of Lévy processes, this becomes more transparent, much more transparent than the result by Goldie. Okay. So for instance, we can use Smith's renewal theorem that tells us that the behavior of this convolution as t goes to minus infinity when the mean is finite converges to the integral of f with respect to Lévy measure to describe the asymptotic behavior of this, okay? Either at 0, okay, or at infinity. And there is more. There is also stone decomposition, and stone decompositions that give us information about the rate of convergence of this. Okay? So using these facts, we can get results of this type. So for instance, if we have that psi satisfies the Cramer condition that is given here, and this integrability condition, so if we have m equal to 1, it's sufficient to ensure that this term here is going to this one. Okay? But if we ask for a little bit more, then we can get the rate, and we will get that the rate is like 1 log of n to the power f minus 1 to the t. Okay? And when there are exponential moments of any order, like in the case where psi is spectrally negative, we'll see that the order is 1 over t. Okay? In fact, the best we can do in this order will always be 1 over t. Okay? If not, we will have a logarithmic rate. When q is strictly positive, we can also get that this decreases linearly. When q is equal to 0 and psi is not spectrally positive, so there are, the process has some negative jumps, then we will have that if the tail Lévy measure of the downward ladder height subordinator is close to exponential, so it satisfies this condition here, then the behavior of I, the distribution of I close to 0 decreases like this integral in terms of the downward ladder height, and it can also be written in terms of the Lévy measure of psi. Okay? But there is a recent paper by Madden and Pierre where they study the case where psi is spectrally positive, and they get some very precise estimates for this other case. And I don't know how to get those estimates yet from this equation. Okay. So now in the final part, let me tell you some stuff about the Markov additive processes, okay, and the extensions of the results. So for defining a Markov additive process, we'll be considering a Markov chain, JT, which is living in continuous time in a finite state space E. We can work in more general spaces, but I won't speak about that at the moment. And we'll say that a couple psi and j is a Markov additive process. Okay, if the joint process is strongly Markovian, that is the first condition here, and the second one is that the increment of psi t, or psi t plus s minus psi t and gt plus s, given what has happened up to time t, okay, has the same law as psi s and js, but now starting at the position at time t in j. Okay? So the first coordinate will be starting at 0, and the second one will be starting at the position where we are at time t. Okay? So to get a clear idea of what this process is doing, just imagine you have a process with one dynamic, so one Lévy process psi, so psi 1. Okay. The process will move like psi 1 while the Markov chain G is in state 1. Okay. Then it will switch at some time T1 to a state, J will change to a state -1. T1 is equal to -1, and from there we will make a jump to a random position that will be given by u1 -1, and from there the process will move as a different Lévy process with a dynamic psi 2, and then when the Markov chain changes again to the position, let's say 1 again. So imagine the state space of J is just -1, 1. Okay. So we make another jump and we continue with the dynamic of psi 1. Okay, and so on. Okay. So this is a way to build the process, the Markov additive process. So it's what is being said in here, and I am interested by the exponential function of this Markov additive process psi. Okay? And the reason for that, well, these Markov additive processes are characterized by the characteristic exponent, okay? But now the characteristic exponent is a matrix. It's a matrix wherein the diagonals are the characteristic exponents of the Lévy process. And of the diagonals are the distribution of the jumps, okay, and the rates. And there is also a formula for the characteristic of psi. Looks as before, but just is an exponential matrix. Okay? And the reason why I'm interested in that is because there is a connection between these Markov additive processes and real-valued self-similar Markov processes. That is given by the Lamperti-Q transformation. So this tells us that if we take X, that is a real-valued self-similar Markov process killed at the first hitting time of 0, then X can always be written as the exponential of psi multiplied by J, and psi and J are a Markov additive process, but there will be time change by this additive functional, so by this random time, okay, that is accelerating the path when the process is close to 0 and decelerating the path when the process is close to plus infinity. Okay. And yeah, that's it. So any self-similar Markov process in R can be written like that. Killed up to the first hitting time of 0 can be written like that. And then, sorry, for this exponential functional that we have here, which will represent the first hitting time of 0 for this process, okay? And it's not the only connection, it's also related to entrance laws and to other properties of these processes. We have a similar formula as before, so we have the detailed distribution, but now we need to write that in measure form, okay? So we have that the measure which has a density given by the tail distribution of the exponential function of the map, starting from the state I in the Markov chain, should satisfy this relation. So I need now to write the potential measure of the process I and j. Okay? It's just again because of the Markov property in the proof. When there is a density, we look as before. Okay? And if we integrate each of these sides, we'll get a moment formula like the one in Carmona, Petit, and York. Okay? And using, for instance, the Markov additive process, the Markov renewal theorem, we can also get the tail distribution of I when the map satisfies a Kramer type condition. I will not describe now. And well, in the work in progress with Andreas Cipriano, his student Rapat, we are studying, we're trying to determine what is the form of the residual exponential functional associated to the exponential functional of the map. And we are also trying to get an idea of the factorization of Pierre and Mladen for maps. Okay? And well, we have already some a preliminary version of it, but it's still a bit rough. Yeah, that's it. Thank you very much for your attention.
Thanks a lot, Victor, for a complete view about this factorization. Are there any questions or remarks?
Say something about this integral potential equation of Markov.
Yes, yeah.
They claim in the paper that the function of density is infinity. Yes, they claim in the paper that the function is infinity. You put it here. But I have a response to people that this is not true.
Yeah.
Can you try to see to check that proof because I think it's not there.
Yeah, you're right. Yeah, I at some moment I went through the proof, and it's true that there was something that was delicate in there. Yeah, so, yeah, this infinities was not that clear there. And yeah, there is a gap in the proof. Yeah, that's true.
I also want to ask you how did you get the Markov quality post to get the factorization?
We're still working that. There are some tricks. I mean, because it's a matrix factorization, so it has to be done a little bit more carefully. But we have some ideas of how it should look like, but there are still a few things to be done.
You mentioned the analog of the exponential functional. When you integrate the exponential of one Lévy process against another, is it known about moments of such a quantity?
Not that I know. I tried to do some stuff. I couldn't get something a recurrence relation. I mean, if you do it for once, you can do some stuff for the first moment, because you can use some martingale argument. But for more general, I don't know how to do it. I don't know.
Second moment.
There are some cases where the moment you find a functional equation that's the transform satisfied in the case where the driving
yeah, it becomes each time it's more involved. Yeah.
Seems like.
So you have this thought about the power tail of the function.
Yeah.
How does this extend to the multivariate case? We have instead of one, we cross two. We have the two-dimensional exponential function.
Yes. I never thought about it. I mean, possibly.
The fluctuation theory is not well developed in one-dimensional case. That's the problem. The way the factorization almost is no good theory there. It may be a one-dimensional theory.
Yeah, I don't know. I never thought about it. I don't know actually if that can be done with the classical theory of perpetuities.
All right, but that's a different story. You can get sort of better result with a more transparent with the rate of convergence.
Exactly. Yeah. But, I'll try to have a look to first to the perpetuities and then to see.
Are there any other interesting questions?
Well, there can be. All questions are interesting.
So if not, let's thank Victor again.